Okay, so we're going to do some more entropy stuff. Today what I'm going to prove is something about homomorphism densities. So you might remember this from like chapter 4. We're going to prove that for any tree with at least two vertices, the homomorphism density, and any graph G, the homomorphism density of T in G is at least the homomorphism density of K2 in G to the power of the number of edges in the tree. So you might remember we proved very similar things for like even cycles, and I think in one of your assignments you proved a similar thing for complete bipartite graphs. So we proved, for example, C2K, the density of an even cycle in G is at least the density of K2 raised to the, 2K, which is the number of edges in the cycle. And in assignment 4, so this was in class, in assignment 4, there was also KST, the density is at least the edge density to the S times T, which is again equal to the number of edges in KST. Okay, so we're proving like an analogous thing for any tree. Okay. For this, we're again going to use entropy, but we're going to need a property of entropy that we haven't used yet. So let me explain that now. So this property of entropy is related to like what happens when you have variables that are independent. It kind of, one thing is like, if you have variables that are independent, then like, if you think about it, let's say x and y are independent. If I learn the outcome of x, then that gives me a certain amount of information. And if x and y are really independent, then that should not influence how much information I'll get from learning y, right? Basically, learning the outcome of x just doesn't tell me anything about y. And so that's the kind of thing that we're going to need. But we also need this in a sort of conditional sense. So we'll have to talk about conditional independence. Suppose I've got three random variables, x, y, and z. So we say that x and y are conditionally independent given z if basically the idea is going to be that no matter what z is, like the probability that x is equal to something given that y is equal to something will not depend on, let me just write it. So the probability that x is equal to little x given that y is equal to y and z is equal to little z. So I want to say basically in the presence of the, given that we know the outcome of z, I want to say given this outcome of z, x and y are independent, which means the probability x is equal to x given y is equal to y is just the probability x equals x. But then given this, so So basically we can remove this y equals y thing. So this is kind of like in the presence of this information, x and y are independent of each other. And similarly, so we need kind of two things, this and the same thing with x and y reversed. And this should hold for all z in the range of capital Z, x in the range of x given that z equals z. So in other words, it's all the little x's that x can equal given that z equals z, and all y in the range of y given that z equals z. Okay. In kind of layman's terms, what this says is, yeah, the probability that x is equal to any particular value, given that I know the outcome of z, this probability is not influenced by learning the outcome of y. Basically, knowing some sort of value for y, it doesn't affect the probability. It's as if we didn't even know it. In our application, it's going to be clear why this kind of property holds, but yeah. Let's recall this kind of deconditioning lemma for entropy. And I'm going to add like an extra sentence to it. So this deconditioning lemma says that if I have the entropy of x given y and z is at most the entropy of x given z. And I may have written it with different symbols in different places before, but this is what it basically says. So knowing y and z can only decrease the amount of information I get from learning x, right? Already having this prior information is more prior information than this. And what I want to say is equality holds in this inequality if and only if x and y are conditionally independent given z. And thinking about this in terms of information maybe makes sense, right? What we said before is if I already know the outcome of x and y, and then I want to say how much information do I gain from learning x, that should be less than or equal to as much, the information I get from learning x after only knowing z, unless knowing y doesn't actually tell me anything about x, right? And that is really what this conditional independence means, right? So yeah, this kind of tells me possibly more about x than z does, unless y doesn't tell me anything, given that I already know z. So yeah, and it's not hard to prove this like formally, again, using like Jensen's inequality and the fact that x log x is convex. But anyway. Okay, so let's try to prove this theorem now. And this is a little bit different than other applications of entropy we've seen. Because actually, I think in most of the applications, oh no, not necessarily, but yeah, in a lot of the applications we've seen, we've picked a uniformly random object and then estimated its entropy. This time we're going to pick a homomorphism of T into G in a non-uniform way, and then bound its entropy from below. So let's get into the theorem. So let G be a graph. We can assume it has at least one edge. This is a kind of stupid condition, but I mean, if it didn't have an edge, then the inequality is definitely true, because both sides are 0. Okay, if it doesn't have an edge, then something I'll write down will be dividing by 0, but we can assume it has at least one edge, right? Pick an arbitrary root in the tree. So this is a root, like this is a vertex of the tree. And for any non-root vertex, let's say S in the tree minus the root, the parent of S, which we'll denote by P of S, is the unique neighbor of S that's closer to the root than S is. So it's the unique neighbor of S. In other words, so on a path from S to the root. Okay, because I mean, in a tree, right, like between any two vertices, there's a unique path. So yeah, if I think of my root as being at the top, obviously all trees are rooted from the top. Not except in real life where they're rooted from the bottom. If this is my vertex S, right, then this would be its parent. You just go up one level of the tree. Okay. So I'm going to construct, so this is my tree T. I'm going to construct a homomorphism from T to G using a sort of randomized algorithm. So we construct a homomorphism F from T to G randomly as follows. Okay. So first I'm gonna pick where the root maps. Now, like a sort of natural thing to do is to pick a uniformly random vertex for the root to map to, but I'm not going to do that. It's not going to be uniform. So, okay, so first pick f of r, meaning, so the homomorphism is called f. So I'm picking an image for the root. with this kind of probability. So the probability that f of r equals v for some vertex v of g is going to be equal to the degree of v divided by 2 times the number of edges of g. So this is like going to be a sort of biased choice where we're biased towards picking vertices with higher degree. And note that this is not dividing by 0 because you've got at least one edge. And also notice that this is well defined because these probabilities do add up to 1. Because if I sum the degrees of the vertices, it's 2 times the number of edges, and so it cancels and makes 1. So this is like a well-defined first step, I think. And then we basically will go through so okay, if we've got this parent kind of relation, you also have like a child relation. If something, S is the child of its parent. And now basically we'll go through the children of the root. And if we're trying to make a homomorphism of a tree to G, I guess the question is, where should I map this child of the root? Well, it's got to go to a neighbor of where the root mapped, right? It's got to go to a neighbor of f of r. And we may as well just pick a uniformly random neighbor. And we can do that for each neighbor of the root. And remember, in a homomorphism, we're allowed to map 2 vertices to the same place. That's not a problem. So we can do this independently for each vertex. So basically, for each S in the tree that's not the root, map S to a uniformly random neighbor of f of its parent. So I guess I'm implicitly assuming I'm going through this tree kind of in levels. Just pick these things in the order where for every vertex I do it after its parent at some point. And do this independently of everything we've done before except for the choice of where the parent mapped. Because of course that's the choice of f of s is obviously dependent on the parent because it's a neighbor of it, but just make it independent of everything else. So independent of, basically all other choices, right? Okay, I'm being a bit kind of lax here about talking about the independence, but obviously it's not independent of its parent, but it's basically we're doing a random walk, right? I pick a random vertex with some distribution. The neighbor, I just pick a random neighbor. This one, I just pick a random neighbor of that, which could, by the way, go to the same place as the root, right? There's no restriction on that. This vertex here might just map to the same place as the root. Totally fine, because this is being sampled independently of everything I've done before, except that it must be a neighbor of this one. So it's basically constructing this tree like a random walk in the graph. Take a random step, etc. That makes sense? Okay. So now let's recall some property of entropy, that the entropy of a random variable is at most the log of its range. So in other words, the entropy of f, where f is my random variable, right? It's a random homomorphism. is at most the log of the size of the range of f but of course, like the range of f, I mean, it's going to be, all the homomorphisms, the set of homomorphisms from T to G. Okay. So this kind of clarifies what we want to do, because I mean, this function here, right, this homomorphism density, I mean, it's basically the same thing as the number of homomorphisms, just normalized, right? So, sorry about the, yeah. So it's a lower bound, this number, which is essentially the same thing as the density. Oh, thanks. To lower bound, the number of homomorphisms, it suffices to lower bound this entropy. Okay. And that's what we're going to focus on. Okay. And this function, by the way, you can think of it as like a tuple, right? I mean, you can think of the h of f as being the same thing as h of the tuple that records the images of all the vertices of the tree, right? So this is the type of random variable that we're quite good at dealing with, because we can use things like the chain rule and stuff. Okay, let's actually do it. Let's use the chain rule right now. So well, okay. Actually, yeah. Let's assume that let's assume that I want to put an ordering on the vertices. So order the vertices of T by let's say S1, S2 up to Sk. Let's say it has k vertices, where S1 is the root, and for any vertex, the parent comes before that vertex. So for any S in the vertex set, PS comes before S. Okay, if you think about any specific tree, it's quite easy to do that, right? Just label the root as the first one, then go through its children, and then go through their children, and then go through their children, and that'll give you a labeling, right? Okay, so let's look at this entropy. So by the chain rule, I can split this up. I can take the entropy of the first vertex, which is the root. So the entropy of the image of the first vertex. Okay, and then I can sum over I from 2 to k of the entropy of the image of the ith vertex given everything that came before it. So f1, f of s1 up to f of s I minus 1. Okay. But now, this is where conditional independence comes in. You know, the way we chose the image of any vertex that's not the root, so this is the root, it's kind of separated here. These are all the non-root vertices. The way we chose the image of any non-root vertex was just a uniformly random neighbor of the of its parent, right? And that was done kind of ignoring the images of anything else except for the parent, right? We did it independently of that. So, you know, for any s, so f of, basically I want to say that this random variable is conditionally independent of all of these except for the parent, given the parent. So therefore I can just delete everything here except for the parent, the f of the parent of si. Which if we write it in another way, this is, so we still have the entropy of the root, and then we sum over all I equals, or actually, writing this in another way, we sum over all the vertices that are not the root. So I'm now getting rid of this ordering in some sense. And we have the entropy of f of s given f of the parent of s. Okay, and this is by conditional independence. Okay, so this is very sensitive to like the actual way we constructed this thing, right? Okay. And yeah, these are all actual equalities because yeah, you have the independence, so it's not even, yeah, it's not just a bound. So next what I'm going to do, so we basically applied the chain rule to split it up. We've applied conditional independence to sort of simplify things, to get less conditioning. Now I'm going to apply the chain rule in the reverse direction to represent this differently. So, like, what do I mean by that? So the chain rule would tell me that the pair, the entropy of the pair f of s, fp of s, is equal to so I'm separating out this one and then doing this one given that one. So so this is just the chain rule, right? But if I solve for this, you know, this is equal to this thing minus that. So my, you know, the entropy of f I can now rewrite as the entropy of the choice of the root. Remember S1 was the root. Plus the sum over all non-root vertices of the entropy of f of s, the pair f of s, f of the parent of s, minus the entropy of f of the parent of S. Okay, so all I'm doing is taking this thing and substituting using this equation. Okay. I don't know if I might have been missing a bracket there. Anyway, yeah, so this is using the chain rule kind of again. Okay, I guess an important thing at this point is to determine what is this. So I guess the question is, what is this entropy? The entropy of, like, the choice of the image of some vertex of the tree and its parent. I mean, in fact, this is just an arbitrary edge of the tree, right? Every edge in the tree is like some vertex and its parent, right? So let me just say, what is the entropy of, wow, that's extremely close, right? I can see them like right out the, anyway, they're gone now, but yeah, so what is this entropy for some edge of the tree, right? So maybe let's call these vertices S and T. I want to stick to, I want to be consistent to like use U and V for vertices of G and S and T for vertices of T, but anyway, sorry about that. So now we're going to use a sort of magical property of the distribution that we chose. So I claim that for any edge of the tree, the pair f of s, or yeah, well, yeah. If I just look at this random pair of vertices, so is a uniformly random pair of adjacent vertices of G. Meaning, like, basically, yeah, for any pair of adjacent vertices in G, for any UV, this has an equal probability of being equal to any possible edge, right? So proof. So let UV be an edge of G. Okay. Let's first consider the case suppose that one of our vertices is the root of the tree. So the edge we're looking at is RT, for some neighbor of the, some child of the root. So I guess what is the probability that f of r is equal to u and f of t is equal to v? Okay. Well, I can compute this directly. I mean, using basic probability rules, this is the same as the probability that f of r is u times the probability f of t is v, given that f of r is u. Now I can substitute for these two things, right? Do we remember what, like, I've erased it now, but what this should be? So the root had some special kind of distribution, right? It's just the degree of u over 2 times the number of edges, right? So that was like the first step of our kind of random choice, was for any vertex, the root maps to that vertex with this probability. But then what's this probability? Yeah, because like that's how we chose things, right? We once you know where the root goes, you put its child on a random neighbor. So each neighbor, because v is a neighbor of u, each neighbor had probability 1 over d of u. And then lo and behold, you know, these cancel. And it just gives you 1 over 2 times the number of edges. And this is true for every single adjacent pair. And of course, like the number of edges is e of g, and then like the number of adjacent pairs is 2 times that, because you can flip it either way, right? So at least for something that's adjacent to some edge that is incident to the root, it has the right property. But now basically, I mean, you can kind of do this maybe by induction on the distance of that edge from the root or something. But basically now all I need to show is that, like, what is the distribution of t? And I want to show that t has the same distribution as r. And then for for an edge that's like this, you could just apply the same argument to that edge if t has the same distribution as r. So now for any vertex v, let's say, or u, I don't know, v. So what I want to compute next is the probability that f of t is equal to v. And I want to show that this is that basically t has the same distribution as the root, right? I want to show that this is equal to the degree of v over 2 times the number of edges. So we're going to do this as follows. Let's sum over all the neighbors of v. So the probability that t maps to v is the same as the sum over all the neighbors, the probability that the root maps to u, and t maps to v. But we already computed that, right? We literally just computed that for any u and v. So this is just, and the number of things in this sum is the degree of v. So that's d of v over 2 times the number of edges. Okay. And so what this tells you is that actually the kind of distribution on t, the probability t is equal to any given vertex, is the same as for r. So now if I wanted to prove this for some edge that looks like this, connects to t and not to r, I would just use the fact, I would do the same thing. I would replace this by a t and this by whatever other vertex, and everything would work out. So yeah, every vertex of the tree actually has the same distribution under this kind of this map, this distribution, this random homomorphism. Does that make sense? So So this maybe is not a full proof, but you can just say kind of by induction in some sense. You could, it propagates throughout the tree. Okay, well that's kind of useful because actually what is a uniformly random pair of adjacent vertices? That's the same thing as a uniformly random homomorphism of K2 to G. So coming back to this question, what is the entropy of this pair? I mean, this pair is just a uniformly random pair of adjacent vertices. So the answer is that this entropy is equal to the log of the number of homomorphisms of K2 to G. Because again, this is just a random pair of adjacent vertices. That is, and like the images of the two vertices of K2 here are also just a random pair of adjacent vertices. It's the same distribution. And for a uniform distribution, the entropy is equal to the logarithm of the range. So actually, like, we're kind of pretty much done here. Well, so actually what we've got so far is that the log of the number of homomorphisms of T to G is at least the entropy of F, which is equal to, now if you think about this, if I kind of rearrange this a little bit, well, so, I mean, like we said, every vertex has the same distribution as the root vertex does. And every edge has the same distribution as well. So it's like, what this really is the number of edges of the tree times log base 2 of the number of homomorphisms of K2 to G. Okay, this is, what I'm doing here is taking account, like I'm counting up these terms, right? So for every non-root vertex, like that vertex and its parent, if I sum that over all the vertices, that counts the number of edges. And then this is always just equal to that, right? So I'm just replacing that. And then I want to say, so all of these things are the same thing. And then I've got this one. If you think about it, that's the number of edges of the tree minus 1 times the entropy of the root vertex. And again, that's because like every vertex has the same distribution, so they all have the same entropy as the root. So I'm just repeating the first term here. For the second term, the number of edges minus 1 in a tree is equal to, oh, sorry, yeah, what am I doing here? No, yeah, seems fine. Okay, so this, this, the entropy of the root vertex. The thing is, like, so the range of this random variable is just like all the vertices of G. So I can upper bound this entropy by the log of the number of vertices of G. Okay, because, yeah, this, yeah, the range of this, I mean, is at most all the vertices of G. And basically now do some rearranging, and it will give you that the entropy of, or sorry, the homomorphism density. So, I mean, this is the number of homomorphisms. This gives us a bound on that. And now, basically, all I'm saying is divide that by v of g to the power of the number of vertices of t, do some rearranging, and if you take my word for it that, you know, this does give you this in the end. So yeah, maybe I won't do all that algebra, but yeah, using your kind of logarithm rules, getting rid of the logs, and then like just dividing by the right thing, yeah, it gives you the bound that you wanted. So yeah, that completes the proof.